In this video, I will introduce how to use limma to find differentially expressed genes. This video contains 4 parts: introduction to limma, installation of limma, and the last 2 parts is about how to use limma into different experimental design settings. Limma is short for linear models for microarray and RNA-seq data. When we test the difference of gene expression level in small samples, we are troubled by the problem that we cannot get a good estimation of variance. The advantage of limma is that it can use empirical based method to borrow information from all genes to provide stable variance estimation. First, let's install limma. It's quite easy and straightforward. You can fetch limma from biconductor. First, you can source the bioclide function and then use bioclide to install limma. After we have installed limma, we can start our analysis from single factor design. Single factor design is an experiment design which has only one factor that will affect experimental result. For example, if we choose 3 tumor samples with jerk and use another 3 non-treated samples as control and keeping all other conditions the same, the only factor that will influence gene expression is the treatment. Thus, we call it single factor design. And here we can define yi as the expression level of one gene in sample I, t the mean expression level of treated sample tumor, which is cases, and mean expression level of non-treated tumor sample, which is controls. We can write yi as like this. And the big I is an indicator function. And for example, if it's a tumor sample, then I tumor will be 1 and I normal will be 0. Thus, we can write yi for the 6 samples like this. We could also express it into matrix form, and we call this one the design matrix because it is stored experimental design information. To compare gene expression level in treated samples and controls, we would like to compute t minus n and test whether it is significantly different from 0. And for t minus n, we could also write it into matrix form, and we call this part the contrast matrix because it specifies contrast of interest. Now let's do it in R. First, we need to design contrast to create a design and contrast matrix. We can do it by hand. It's quite intuitive. The only thing we need to do is to input the above matrix into R manually, and then assign column names to it. It's our design matrix with column name, and it's our contrast matrix. We could also create them with function provided by limma. To create design matrix, we can use model.matrix. First, we store our sample information into a variable. Then we transform it into a design matrix using model.matrix. Look, here we use 0 because we do not need an intercept for this linear model. And then we assign column names to our design matrix. It's how our design matrix look like. It's exactly the same with the one we input by hand. The only thing different is that one is a matrix and this one is an object, and then we can use it to construct our contrast matrix. We make a contrast to construct our contrast matrix. Since we are comparing case and control, we write here case minus control and assign name DIFF. You can use any name here, like DEG. And then we give the names of the parameters to be contrasted, and by passing design matrix to levels parameter. And this is how our design matrix looks like. To fit limma, we have three major functions. The first one is lim fit. We use our expression data as input, and then another input is design matrix. It will fit linear model to estimate T and N for each gene. Then we use contrast.fit. It takes the fit object produced by limfit as input, and also the contrast matrix. It will fit a linear model to estimate a set of contrast, for example, T minus N. And then in the third step, we use eBase. It takes fit object returned by contrast.fit, and it will compute moderated statistics using empirical Bayes moderation of the standard errors. Now let's see the code. First, we use limfit to estimate parameters, and then use contrast.fit to estimate the contrast parameters, and then eBase to modify our statistics. Finally, we report our differentially expressed genes with top table. The first input is the fit object returned by eBase, and we set coef as DIFF because DIFF is the name we assigned for our contrast. We'll see more in the two-factor design. We set our p-value as 0.05. Since we are simultaneously testing 57 genes, we have to correct multiple hypothesis testing, and the common method is the FDR. LFC is a log2 fold change, so if we want to have genes with fold change larger than 1.5, we need to assign log2 1.5 to LFC. Number is the number of genes that the top table will report. The default set is 10, but we want to assign it with the total number of genes. Finally, we get 292 differentially expressed genes with fold change greater than 1.5 and adjust p-value less than 0.05. Now let's talk about two-factor design. Suppose now we have 12 samples and 3 cases and 3 controls in treatment 1, 3 cases and 3 controls in treatment 2. The gene expression level now will be affected by 2 factors. First, whether it is in treatment 1 group or treatment 2 group. Second, whether it's a case and control. We can express yi like this. And the process of design matrix is similar with the one-factor design. First, we store sample information to a variable and then transform it with model.matrix, similar with one-factor design. It's also 0 here because we do not want to include an intercept. And then we assign column names. And here's what our design matrix look like. Since we only have the first 3 samples as cases of treatment 1, so we only have 1 for the first 3 samples, and the others are all set as 0. It's the same for the other 3 types. And then we construct our contrast matrix. It's a bit different from the one-factor design. Now we have 3 sets of contrast. The first, we want to get DEX for treatment 1, so we compare the case in treatment 1 and control in treatment 1, and it's the same for treatment 2. And sometimes we want to get genes that respond differently to the 2 treatment, so we compare the expression level change in treatment 1 and the expression level change in treatment 2, and this is how our contrast matrix look like. Finally, we fit limma. It's the same with one-factor design. First, we use limma fit to estimate the parameters, and then we use contrast fit to make a comparison, and then we use e-base to modify our statistics. And to get the DEX for T1, we assign a coefficient as T1, and for T2, we assign it as T2, and for the differential response gene, we set it as DIFF. Finally, we get 291 differentially expressed genes for treatment 1, around 600 for treatment 2, and 8 genes that respond differently to the two treatments.